Check it out now, y'all.
NanoHub U, online instruction.
In this lecture, we'd like to begin a sequence of lectures which discuss the nature of the electron energy states that are present when you bring together a collection of, let's say, 10 to the 20 some atoms. The discussion we're going to conduct in this lecture is going to be somewhat qualitative. We're going to just basically count electrons on our fingers, and we'll find that following this approach, we can understand an awful lot about the nature of electron states that develop when you bring together these different atoms. So the way the lecture is structured is we're going to talk about the transition from atoms to crystalline solids, and we're going to introduce the concept of an energy band, and we're going to try to figure out whether the energy band is completely full or partially filled simply by counting electrons that we know about from the atomic states of atoms. And then we're going to introduce the simplest model that we can imagine, which is a one-dimensional free electron model to describe the quantum wave functions of the electrons when they're in a solid. So that's the program. The concepts are pretty important, so and they're also reasonably easy to understand. So I think if you don't get this lecture, then the next 3 or 4 lectures are going to be very confusing. So this is one that you should pay close attention to. And to begin with, let's review what we've already discussed, right? We've already discussed the quantum states that develop when you confine electrons to a nucleus, right? The nucleus has got Z protons, and surrounding that nucleus have to be Z electrons. The atom is electrically neutral, of course. And what we've discovered by investigating Schrodinger's equation for this particular problem, we've discovered that these energy states inside, the electron energy states inside this atom, take on this quantized structure, okay? And so we're going to assume that that's reasonably well understood, that in principle, detailed calculations provide us with the energy levels of these different electron states, right? And of course, these electron states are designated as S, P, or D, depending on the quantum index script L that's appropriate. Now, what happens if we have a collection of these individual atoms and then we slowly bring them together to form a crystalline solid? Well, in principle, the discussion should be conducted in 3 dimensions because these crystalline solids fill all space in 3 dimensions. Unfortunately, the intuition gets quickly lost when you extend a discussion into 3 dimensions. So what I'd like to do for the purposes of just understanding what's going on, I'd like to just consider a one-dimensional row of atoms. All the arguments translate into 3 dimensions, but it's much easier to see what happens in a one-dimensional picture. So in 1 dimension, if we assemble a group of atoms, ultimately the atoms are going to be spaced one apart from another by this distance A. We're going to assume that the solid crystallizes into a crystalline solid, which simply means that every atom is spaced from every other atom by a distance A. We're also going to assume that all the atoms in the crystalline solid are identical, so that the electron energy states of the individual atoms are all the same. Now, something very interesting happens, right? It turns out this separation distance A is on the order of a few tenths of a nanometer. And what that simply means is that for most crystalline solids, and in particular for most metals like copper, silver, gold, magnesium, zinc, right? For most of those simple metals, the electrostatic potential energy of one atom starts to overlap with the electrostatic potential energy of the second atom. And this just simply means that the electrons are now going to see an electrostatic potential energy, which is the sum of the two separate curves from each individual atom. And the sum of those two curves is going to actually drop the confining potential of the electron to a new value, which I've schematically indicated by this dashed line. So if you're an electron energy state and you're down here tightly bound to the nucleus, right, this shift in the electrostatic potential energy that occurs because this distance A is so small, that shift doesn't affect much these states that are buried deep down here. But these quantum states that are located near the top of this electrostatic potential energy well, they're going to be dramatically altered because the barrier is going to be lowered. In fact, these electrons, which used to be confined to a separate individual atom, now find themselves in an extended potential well, and gives rise to a situation in which they can become delocalized from the individual atoms. So the effect that I just described is indicated schematically in this particular picture, right? These tightly bound states down here, we call these core states. They may shift slightly in energy, but they're not gonna drastically change their location and energy. These energy levels are, of course, have to be governed by quantum statistics, and we've already discussed that. Since electrons are fermions, at most you can get 2 electrons per energy level in each of these quantum states for the individual atom, right? The electrons in the uppermost energy states are basically going to become now delocalized because this potential well between the individual atoms is depressed. And when you depress that potential well, the electrons find a region where they're free to move around, right? And so they can become delocalized over the entire crystal. So these states these red states that used to be localized to the individual atoms now become delocalized. Their energy states, the location and energy of these states also shifts slightly, right? So each state can still only hold 2 electrons, and so there becomes a ladder of states, as indicated by this continuous region of red. And each state in that region can only hold 2 electrons, but the state is now delocalized over the entire crystal structure. So there are some important new parameters that are defined based on this discussion. One parameter is this so-called work function of the metal, right? This work function is the distance between the highest energy occupied state in the solid and the zero of the electrostatic potential energy. So this is the famous work function from the photoelectric effect that we discussed in the first week of the semester, if you recall back then. And the other important term is to understand what we mean by the word valence electrons. Very often the word valence electrons refers to these highest energy states, right? These are the states that become delocalized. And when we talk about valence electrons, we want to know how many states per atom have undergone this transformation to the delocalized situation. So these are weakly bound to individual atoms. They're basically reorganization due to the fact that the electrostatic potential energy between the atoms is dramatically altered when you bring the atoms close together. So to try to illustrate these ideas, let's focus on one specific example. The example I pick is copper, because copper is known to be a good conductor of electricity. And so what we need to do is we need to know something about copper. Well, copper has 29 electrons. It has 29 protons associated with it. And these electrons fill up these energy shells according to the structure that I've got indicated here. The highest, the most energetic electron in copper, in a copper atom, the most energetic electron in a copper atom occupies the 4s level, and there's 1 electron in that 4s level. There are 10 electrons in the 3d level. So the 3d level is filled. The 4s level is, in principle, it could take 1 more electron. So what I like to do is I like to call the valence of copper 1, which indicates that there's this 1 electron which is going to be delocalized and reorganized when you bring copper together. So in principle, in 3 dimensions, you can do X-ray crystallography experiments, and you can convince yourself that copper crystallizes in this face-centered cubic structure. This face-centered cubic structure turns out to have 4 atoms per unit cell. And the way you get 4, I mean, if you just count, right, if you just count the number of electrons, you might think, or count the number of atoms in the unit cell, right, there's 1 on each corner, so there's 8 atoms on the corner, and then there's 6 faces, so you might say there's something like 14 atoms in that unit cell. That's an incorrect calculation, because the atoms on the corners are shared by 8 adjacent unit cells, so there's only 1/8 of an atom in each corner. So there's 1 atom total that occupies the corners of a unit cell, and then likewise, half of an atom occupies the unit cell on the face, because there's an additional unit cell not pictured here, which shares the other half of the atom. So you end up with 6 faces times 1/2 gives you 3. So there's 3 atoms on the faces, there's 1 atom on the corners, so there's a total of 4 atoms per unit cell. If we look at very careful calculations of the electron energy states when these electrons are, when these copper atoms are organized into this face-centered cubic structure, right? If we look at very carefully those energies, we get numbers that appear in this table here. And the point I want to make is that these lower energy states, the 3p's and 3s electrons, these electrons are hundreds of electron volts below the Fermi energy of copper. Right? The Fermi energy of copper just specifies the most energetic state that an electron in copper can have at 0 degrees Kelvin. And the 2 uppermost states, the 3d and the 4s electrons, they're separated by about 2 electron volts in energy. Certainly the 4s electron lies right at the Fermi energy, and the 3d electrons lie about 2 electron volts below the Fermi energy. So what does that mean? Right? That means that if we try to indicate the position of these electrons inside of a copper metal, we end up with a picture that kind of looks like what I've drawn here, right? There's a work function or a barrier that prevents the electrons from copper to spill out into the vacuum. The electrons near the Fermi energy, the most energetic electrons in copper, are going to lie near the Fermi energy, and I've schematically colored them in as red. Below those 4s electrons, you're going to have a band of 3d electrons. I've colored in the 3d electrons in blue, right? And so this picture of a metal, which we first introduced way back in the first week of the semester, now you can start to understand how it comes about. It comes about because these 2 states, the 3d states and the 4s states, those things are reorganized when you bring the copper atoms together to form this crystalline structure. Now, I do a similar calculation like this for silicon in the appendix. I won't have time to go through it in lecture, But I wanted to show you what happens for silicon because it's such an important material for semiconductor people. So that discussion I've just put into the appendix. What I'd now like to do is I'd like to count the electron states in copper, and I want to focus on this 4s level. So the 4s level is going to be at the top of this potential barrier. The potential barrier is going to be lowered when these atoms are brought together. And I'd just like to find out for a one-dimensional line of atoms how many different electron states there are and how many different electrons are available to fill those states. Turns out that's going to be a really important question. So I do the calculation just for 4 atoms so we can do the numbers on our hands, right, on our fingers. And but in principle, you have to do this calculation for n atoms, and in principle, you have to do the calculation in 3 dimensions. But the ideas that we're going to discuss are going to be the same. The numbers aren't going to change, or the results aren't going to change, right? So let's count the number of 4s electrons in our one-dimensional solid, which happens to consist of just 4 atoms. So we know from the atomic states that each atom contributes 1 electron. And since we've got 4 atoms in our linear chain, that means we've got 4 electrons or 4 quantum states that we have to take into account. Each of these quantum states can have 2 spins, a spin up and a spin down. So we've got a total of 8 quantum states available, right? And of those 8 quantum states available, we've got 4 electrons because we got an electron from each of these 4 atoms. So we're putting 4 electrons into a potential well, which basically can accommodate 8 quantum states. And so what that gives rise to is it gives rise to 4 energy levels. Each energy level has got a spin up or can accommodate a spin up and a spin down electron. And if I take the 4 electrons from the 4 atoms and I drop them into these quantum states, what basically happens is I've got a spin up and a spin down electron that occupy the lowest quantum state. I got a spin up and a spin down electron that occupy the next quantum state. And then the 4 additional states, right, because I had a total of 8, right, the 4 additional states remain empty. They're not populated. And so what we say that the Fermi energy is the energy that separates the highest filled state from the lowest unfilled state at 0 degrees Kelvin. And so the Fermi energy is shown schematically in this diagram by the dotted line. And the difference in energy between the Fermi energy and the vacuum level is indicated out here, right? That difference between the Fermi energy and the vacuum level, that's the work function. And that work function is going to determine how these electrons can be photoexcited out by incident photons when we talk about the photoelectric effect. So what we conclude from this discussion, the important thing we conclude is that these highly localized 4s atomic states become delocalized over our crystal, which contains in this slide just 4 atoms. These 4 states that develop form a narrow band of energies, and of those 8 quantum states that exist, only the lowest 2 are filled, and they're filled by the spin up and spin down electrons, as I've indicated in this diagram. So it's really important for you to be able to think your way through this type of problem and to understand these different steps, which on the face of it are pretty simple. But if you can do that, then you basically understand how energy bands form in solids. You can extend the argument to n number of atoms. The only difference is you're going to replace 4 atoms by some number n, which is going to be a large value, right? And what you can convince yourself is that this energy band that forms from these 4s electrons when the copper atoms are brought together, that energy band is only half filled, right? Only electrons actually fill the bottom half of the band. The upper half of the band remains empty. So that's a critical insight that allows you to understand how electricity is conducted by copper, because the electricity is going to be conducted by those electrons near the Fermi energy, right? And they're going to have to be able to access unfilled states in order to move from one region of the crystal to the other. So this forms the basis of an awful lot of very practical electronics, electricity calculations. The next topic is how would we better approximate the electrostatic potential energy U of X in this one-dimensional crystal. So U of X is this very complicated function, right? Close to the position of the nucleus, the electrostatic potential has a very sharp, deep discontinuity. It's not indicated, things don't scale on this diagram. The diagram is not built to, not drawn to scale, but these electrostatic potentials here are very, very deep, thousands of electron volts, right? The topmost electron states are on the order of 1 electron volt wide or so. So clearly this diagram is not drawn to scale on an energy on an energy axis. But what we're trying to do is we're trying to figure out how we might represent this variation in electrostatic potential as a function of position. And there are a number of models that have been developed. The first model that I'd like to discuss is the free electron model. And the free electron model just basically neglects the rapid variation in this electrostatic potential, and it replaces it by some average value, which is indicated by a straight line, which is constant, independent of position. So this gives rise to what we call the free electron model. And the free electron model just basically says if you've got n atoms in a crystal and you put those n atoms close to one another, the electrons from the 4s energy levels for the case of copper are going to be delocalized over this potential well, which is represented by a flat line. And that's very similar to our infinite square well model. Goes all the way back to the second week of the semester. Just remind you of that. The infinite square well model had infinite high barriers. That's not the case for our free electron model, because our free electron model is going to have barriers that have a finite height to them. Nonetheless, the Schrodinger's equation in one dimension that has to be solved is written down here. We have to put in the value for U of X, but we've cooked it so that U of X is 0, and that means that the particles behave like free particles in this well. The consequence of this infinitely high square well was that there are eigenfunctions that are indicated by quantum numbers n. I just list the first 4 here just to remind you. Each eigenfunction has a particular eigenvalue, and these are then the allowed energies of the quantum states in this particular well. There's a slight shift in notation, right? When we talk about electron states in solids, rather than focus on quantum numbers n, we tend to focus on wave numbers k, and we list those wave numbers k with the subscript n to relate them back to this discussion. So when we first discussed this problem back in the second week of the semester, we indicated the allowed energy states in this ladder diagram, right? And the energy states were positioned as n squared, because when you solve Schrodinger's equation, you found that these energies increased as n squared, where n is the quantum index. When we start to discuss the electron states in periodic solids, we get away from this quantum number n, and we focus on the wave vectors k. And so you can define a wave vector k by just rewriting the eigenfunction in a very straightforward fashion, right? So you take out this pi over L, 2 pi over L, you call that a quantum number k, and then what you find is that the allowed energies are just h bar squared k squared over 2m, where m is the mass of the particle. And so now, instead of writing the energy levels in this type of a diagram, we can write the energy levels as a function of this k value, where k is now the quantum index, or the quantum number of the eigenfunctions. And when we do that, what we find that the allowed energies scale as k squared, and so you end up with a diagram that kind of looks like this. And this is referred to as an E versus K diagram, because it's plotting the energy of the electron versus its wave vector k, and it replaces this picture that we've already discussed. So this change in notation is important for you to understand, because from here on out, everything's going to be discussed in terms of k vectors. But in principle, those k vectors can be related back to the quantum numbers n. The virtue of the free electron approximation, or the free electron model, is indicated in this slide. The arithmetic is pretty easy to work through. You write down a free electron wave function which contains this e to the ikx. You immediately realize that the probability of finding the electron in a region dx between 0 and L is a constant number a squared. It just simply means that this wave function is completely delocalized over this entire length of the crystal L. And if you want to find out the allowed energies that this wave function dictates, you have to insert that into Schrödinger's equation. You simplify it to one dimension, because we're just basically doing a one-dimension problem here. And what you find out is that the allowed energies scale as h bar squared k squared over 2m. M is the mass of the electron. And the important thing to remember from this derivation is that there's no restriction on k whatsoever, okay? So that means any k and any electron energy E are allowed when you delocalize electrons in this one-dimensional potential well. And so if I do an E versus K diagram, it turns out to be a continuous parabola, right? And I can have values for plus K and minus K, indicating whether an electron is going from right to left or left to right. So the important thing to remember is any K is allowed and any energy is allowed in the free electron model. The electrons are completely delocalized over the extent of the crystal. And that's what the prediction is. Now that's an approximation. That's clearly an approximation. And what we're going to do in the next set of lectures is we're going to slowly start to correct that approximation. And we're going to do that by including the effects introduced by the periodic nature of the electrostatic potential energy. So this electrostatic potential energy that's approximated by a constant value is going to be replaced by a periodic potential that more closely resembles what we've sketched in some of the previous slides in this lecture. So the next lecture, we're going to define something called the reciprocal lattice. It's a straightforward, it follows in a very straightforward fashion from the periodic nature of atoms in a crystalline solid. So please come on back and listen to that, and we'll talk about reciprocal lattice vectors in the next lecture. Thank you for listening to this one.